First of all, thank you for coming to this talk where we will discuss the security architecture of the Java platform. So just a few short words about who I am. I'm currently working as a software consultant and I'm running my own company called Coffee Cup Consulting. An interesting name for a company. And I'm also one of the guys which organizes the events for the Bulgarian Java user group, where we also have our own community conference. And from time to time, I'm also contributing to the OpenJDK projects and a few other open source projects. I'm also a big fan of RabbitMQ, and recently I finished a book called Learning RabbitMQ, published by Pact. So this is basically what I'm doing. So the aim of this talk is actually to reveal stepwise the architecture of the Java platform throughout the different versions of the Java platform. Also to discuss briefly what are the tools that contribute to the security sandbox model of the Java platform. And at the end, we'll just discuss shortly a few best practices that every Java developer should follow when considering this security model. So let's start with the evolution of the Java security model. And essentially, why do we need security, basically? So as most of you know, many of the companies that are doing any form of development are trying to protect their assets. And by assets, I mean both physical and network assets. There are some companies that are imposing the requirement that all of the communication must be SSL enabled. And also companies are deploying tools such as antivirus software, firewalls, intrusion protection system, and intrusion detection systems. And basically companies are trying to enforce by all means necessary the protection of all types of assets. However, with the introduction of various technologies that allow you to load source code in your browser, and by such technologies, I mean not only Java, but for example, .NET, you have Silverlight, you have Flash, and so on and so forth. A brand new range of security vulnerabilities come up with the loading of remote code in your browser. And basically, the goal of the Java security sandbox model is to allow untrusted source code loaded in the browser to be executed securely in a trusted manner in the user's browser. And basically, the Java security sandbox model applies not only to applets, but basically to source code loaded by, for example, application servers or other types of managed environments, such as an OSGI container and so on. As some of you may know, in Java version 10, applets will be deprecated. So mostly you'll have to develop JavaFX applications if you want to run Java in the browser. But still, applets are a good starting point in order to reveal what does the security sandbox model of the Java platform does. So all starts with version 1.0 of the Java platform, when basically we have the notion of trusted and untrusted source code. And it was that simple. So trusted code was the system source code of the JDK, which was allowed to do anything with the system, write files to the file system, open connections to network sockets, and so on and so forth. And there was the idea of untrusted source code, which was the source code loaded by all of the applets that were running in our browser. So we had just those two types of code. And basically code that was in the trusted domain, as we already said, was allowed to do anything with the system. And all of the other code, such as applets that were loaded in the browser, was restricted and was basically restricted to execute only a certain set of things with the system. However, this seemed not to be quite a flexible model. So in version 1.11 of the Java platform, the so-called applet signing was introduced. And basically, by applet signing, it was allowed for applets to be deemed as trusted. This means that applets had the same permissions as the system code of the JDK. And basically, the process for applet signing was very straightforward. So you had to compile the applet, then create a jar file for that applet, then create a pair of public-private keys, and with the private key, you sign the applet jar file. Then you export the certificate for your public key, and you import that certificate in the as a trusted certificate inside the JVM, which would be running the applet. Then you create a policy file which specifies which permissions does your untrusted code have on the system. And now the system source code along with the signed applets has all of the permissions to do whatever it wants with the system. And finally, you load and run the applet. So this was up to version 1.1 of the Java platform. However, this also seemed quite inflexible. So version 1.2 of the JDK introduced a radical change, which is used up until the latest version of the JDK platform. And that's fine-grained access control. So now you have different places out of which you can load your source applets. For example, you can load an applet from voxxed.com/demoapplet. And this is one location of your applet. So once you have that location that's being set once the applet is loaded in the JVM, you can specify permissions for those applets loaded from voxxed.com/demoapplet. In this particular example, we create a security policy file which basically grants the permission to delete the C Windows folder from the demo applet that we load. And this is one thing. Now, in version 1.2, as you can see, we have defined fine-grained access controls for particular locations of where our applets are being loaded. And not only that, but the security manager and access controller classes are introduced that allow you to impose this permission checking on the applets. So basically, the security manager and the access controller classes do the same thing. And the difference here is that the access controller class is a little bit newer API. And basically, the security manager uses the access controller class to do permission checking. We'll see just in a few moments how this is done in details. So now with version 1.2 of the JDK, the security model becomes code-centric, meaning that we specify permissions based on the location of our loaded applets. And additional access control decisions are specified in terms of Java security permissions that by default are specified in a security.policy file, which stays in the JDK installation. And we already no more have the notion of trusted and untrusted source code that we had up to version 1.1 of the JDK platform. However, instead of trusted and untrusted source code, a new term was introduced, and that's the term of protection domain. And a protection domain is nothing more than the combination of where is the location of that applet. In the previous example, that was voxxed.com/demoapplet. And what is the set of permissions that apply to this applet? For example, it has the permission to delete the C Windows folder. So now we also have two types of protection domains, the system and the application. And the system protection domain was given all of the privileges as we had previously with the trusted domain in earlier versions of the Java platform. And application protection domain is set based upon different permissions that are defined upon the location of where the source code is being loaded from. And a protection domain essentially is set during class loading. So once the class loader loads the particular classes, it sets the protection domain over all of the class instances. And you can get the protection domain by calling .getClass.getProtectionDomain. And out of that protection domain, you can get the set of effective permissions for the class along with the location or the code source of that class by calling .getCodeSource. One interesting thing that is also implied by the permission model of the JDK is that one permission can imply another permission. So if, for example, if we give an applet or some other location of the source code to delete the C Windows folder, this effectively implies that we can also delete the C Windows System32 folder. So this means that one permission essentially can imply another one. And another interesting thing is that also the location of where the applets are being loaded from implies another location. So for example, if we specify permissions for all applets that are loaded from voxxed.com, from that website, this effectively applies that all of these permissions apply for all of the applets that are loaded from the voxxed.com/demoapplet website. Unless, of course, you decide to override those set of permissions. However, as you probably know, one executing source code can pass through different class loaders. And to give you a more concrete example, for example, let's say you have a Java application server and you load a WAR file. As you know, the WAR file is loaded with a different class loader than the one of the application server. And so the source code that's being executed from the WAR file has different set of permissions from those of the application server. And this means that once we do permission checking on the source code of the executing WAR file, we have to do an intersection of the protections domains of the WAR file, of the source code of the WAR file, and of the source code of the application server. So effectively, the permission set of the currently executing thread is considered to be the intersection of all the permissions by all protection domains that are traversed by that executing thread. Okay, moving towards version 1.3 and 1.4, we have a further extension of the security model of the Java platform. Does anyone know what JAS stands for? No one? Come on, what is JAS? Yeah? Yeah, exactly. And you win a book on RabbitMQ. Okay, you can take it after the session. So JAS is Java Authentication and Authorization Service. And the idea behind JAS is to allow for further to be able to specify who is the one that's running the source code. So far until version 1.2 of the JDK, we only had a set of permissions and the location of the source code. But now we have a third dimension, and that's the user that's running the source code. So basically, for example, we can specify that only the user which has a name of Tom can have the permission to delete the C Windows folder. And inside the Java security policy file, this is specified as grant principal. And we have an LDAP principal here. So basically, you can think of a principal as a property of a user. So one user can have one or more principals that specify one or more attributes of the user. For example, a username, an email address, and so on and so forth. In this particular example, the attribute is the name of the user. And by that attribute, we specify that the user that's running the source code or the JAS subject has the ability to delete the C Windows folder. So basically, JAS has two parts, and the authentication part of JAS is not related to the Java Security Sandbox model. It uses pluggable authentication modules to allow you to define different ways of authenticating the user that's running the Java code. For example, you can authenticate the user against a database, against an LDAP server, and so on and so forth. And basically, the authorization part of JAS now extends the protection domain of a particular Java class, not only with the source code from where it's loaded, or basically the code location and the set of permission, but also a list of principals or attributes of the user that's running the source code. So the authentication component, as we already said, is independent of the security sandbox model. And the authorization component is the one that extends the Java security policy file, as we saw earlier here in this example. So that's up to version JDK 1.4. And here is the set of core classes that JAS defines. The interesting thing here is that before we authenticate a user, we instantiate a login context in JAS. And each login context can use one or more login modules which specify an implementation of a concrete login module, for example, for being able to log in against a database, an LDAP server, and so on and so forth. In the standard JDK libraries, we have a few login modules that are implemented for different purposes. So the login context uses one or more login modules to define from where to authenticate the user. And once you authenticate a user, we create an instance of a subject which represents the actual user, which has one or more principals, which are the attributes of that user. For example, username, email address, and so on and so forth. So these four classes basically constitute the most essential part of the GSS API as defined in the JDK platform. So the typical flow for permission checking up to version 1.4 of the JDK is as follows. When we start up our system, we need to register an instance of a security manager. For example, once the JBoss application server starts up, it loads up its own security manager instance. You also need to set a security manager and a security policy file. So basically, you can authorize users based on the permissions set in the Java security policy file, or based on a predefined policy format that you've created by yourself. But typically, this is very error-prone and not very trivial to implement your own policy mechanism. So first, you need to set the security manager and set the location of your policy file. Then during class loading, bytecode verification is done in order to verify that our classes are not tampered with. And after bytecode verification is successful, the current protection domain is set for the class, which constitutes of the code source and the set of effective permissions as defined by the security policy file. So this is the second step. The set of permissions for our classes, our application classes, is set along with the location from where these classes are loaded. And once our classes are loaded and system code is invoked, the security manager is used to check whether the intersection of all of the protection domains of all threads in the execution stack of the source code allows our classes to do what they want to do. So basically, the entire code base of the JDK is filled with security manager.check permission calls, which try to check, for example, whether you are allowed to write to the file system when you create a file output stream, or whether you're allowed to open a socket connection. So for example, this is a very simple snippet that shows you how permission checking can be done. Sorry. So you create a socket permission for voxxed.com between ports 8000 and 9000. Then you check whether you have security manager installed by calling system.getSecurityManager. And if you have a security manager installed, you call security manager.checkPermission and bypassing that permission. So what this simple code does is that it takes the currently executing call stack and checks whether it has the permission to open a connection to voxxed.com on the specified ports. Okay, so once that is done, application code can also do permission checking based on a security manager or on an access controller instance. As we said earlier, access controller is a newer API that provides you with the ability to do permission checking without having a security manager instance installed inside your JDK. And here is the same example, but with an access controller class. As you can see, the code is basically the same, with the sole difference that here we don't check whether we have any security manager installed, but check directly whether we have the permission using access controller.checkPermission by invoking that static method. Also, there are some situations where we need to elevate the privileges of the currently executing source code. So by calling, for example, access controller.doPrivileged, we just skip the protection domains of all of the source code that's being invoked so far until the execution of this piece of code. So this is effectively called privilege escalation. And we can also change the user that's currently executing the source code by calling subject.doUs or subject.doUsPrivileged. And also the security manager API is customizable. So the Java application servers use one type of security manager. And for example, if you want to execute Java stored procedures inside an Oracle database, for example, implements a security manager that checks for permissions defined not in a Java security policy file, but in a relational database. There is a particular database table that specifies what permissions do our Java stored procedures have. So as you can see in this particular example, the security manager is a custom implementation. Okay, so moving towards JDK 1.5 and 1.6, there are just minor additions to the security sandbox model. For example, there is an LDAP support for JAS that is being added, nothing radically new. And in Java 1.7 and 1.8, there are further enhancements to the model, such as, for example, the ability to call access controller.doPrivileged only for a subset of permissions, something that was missing in previous versions of the JDK. And in version 1.9 of the JDK platform, 1.10 and beyond, as you know, there is an effort for the modularization of the Java platform, which is coined under the name of Project Jigsaw How many of you have heard of Project Jigsaw? Okay, I see a lot of people, maybe half of the people. As you know, Project Jigsaw aims to provide the ability to create modules that run inside the Java platform. And as it is specified in the Jigsaw specification, each particular module will be loaded by a different class loader. And this means that each Java module will have a different protection domain, which will have a different code source and a different set of permissions. And as you can see in this particular case, the Java Security Sandbox model will be translated directly to Jigsaw modules without the need to create a more specific security extensions to the current architecture of the Java platform. Yeah, as we said, by modules, we understand modules as they are defined by Project Jigsaw, and basically they conform to the same security model as applets do, or for example, as WAR files do. Okay, so that was basically the security sandbox model that was defined throughout the different versions of the Java platform, and it is being completed by a number of APIs defined by the Java platform. So basically, these APIs fulfill the other side of the coin and allow you to use a number of utilities for establishing security inside your applications. So we'll just go briefly throughout the set of most important APIs defined by the JDK. These are effectively JCA, or the Java Cryptography architecture, the public key infrastructure utilities that allow you to set up and use a public key infrastructure. Also the Java Secure Socket extension, which is just an extension of the standard Java sockets. The Java GSS API, which is an alternative mechanism to the JSSE or the Java Secure Socket extension. And also the Java Simple Authentication and Security layer. So the Java Cryptography architecture provides you with a number of utilities that allow you to create digital signatures, message digests, and all types of cryptographic ciphers as well. And what's important about this API is that it's pluggable. So the JDK just provides an abstract mechanism that allows you to implement different types of algorithms, for example, for creating message digests, for encrypting and decrypting source code. And there are libraries such as, for example, Bouncy Castle that provide particular implementations of that API provided by the JDK. And also the Java cryptography architecture continues to evolve, especially in terms of providing stronger cryptographic algorithms. The PKI utilities, on the other hand, provide mechanisms for working with public certificates, for checking that a certificate that's provided by a certificate authority is valid or invalid. And just as a brief recap on this picture here, you can see what's the flow for checking whether a certificate is valid. You can do this by means of a certificate revocation list that's provided by the certificate authority and specifies which certificates are valid and which not. Or you can use the OCSP protocol for the same purpose. And the PKI utilities provided by the JDK platform also continue to evolve in terms of the support provided by the JDK for managing certificates and keys. The Java Secure Socket extension provides an implementation of SSL sockets for remote communication. It's the secure equivalent of standard sockets as we know them in the JDK platform. And support for the Java Secure Socket extension also evolves in terms of, for example, providing support for creating virtual servers that allow you to create secure socket extension communication between a client and a server. The Java GSS API, very briefly, it's just an alternative of the secure sockets that allow you to exchange security information in terms of a shared context. And basically, the GSS API also provides interoperability with JAS in terms of authentication. And the support for the GSS API in the JDK also continues to evolve, especially in terms of providing more support for security protocols such as Kerberos and a number of others. And basically with the support of their different versions. The Java Secure Authentication layer basically defines a protocol that allows you to exchange authentication data between the client and the server. So for example, you want to establish a secure channel for communication and sharing of authentication data. and the server tells the client, hey, I want to authenticate you with your username, your email and your username. The client confirms this request by the server, and in that manner, basically an authentication channel is established between the client and the server. So basically, this is a framework that allows you to exchange security information between the client and the server. And this API also continues to evolve as well as the other APIs as we saw them earlier. And one of the things that's being additionally provided is more enhanced support for exchanging more types of authentication data. Okay, and in the last part of the talk, I want to discuss briefly on a few good practices that you need to follow based on what we talked about, based on the Java Security Sandbox model and the APIs that we have in the JDK platform. So first of all, most of the guidelines typically do not apply for the Java language only. So you have, for example, type safety, you have input validation, error handling, you have SQL injection prevention techniques. These are all things that are not specific to the Java platform. However, there are a few things that are specific, and one of them is, for example, the fact that you need to respect the security manager. To give you a concrete example, recently I had a case where we had to use the Google JSON library inside a managed environment, such as an OSGI, and the library threw a security exception. And the reason was that basically no permission checking was done inside the library. And when we tried to run it in a security managed environment, such as an OSGI server, there was an installed security manager which prevented the library from using a reflective call. And of course, we had to patch the library in order to provide that support. So if you write a Java library, you definitely need to provide proper permission checks in case there is a security manager installed in the running Java platform. Another thing is that you need to grant minimal set of permissions. There are many cases where developers, just in order to work around a certain problem, grant the full set of permissions to the source code, but this is quite a bad thing for obvious reasons. And another thing is that, of course, if you copy-paste source code, you can translate bugs from the copied to the pasted source code. And this, of course, is not specific to the Java platform. Another thing is that you have to be careful what you show to your users. For example, if you throw an exception and you show the user a stack trace, this actually exposes a lot of information about your system. So you need to make sure that you sanitize carefully your messages before showing them to the users of your system. So that was it. Thank you. I think we have 10 minutes for questions. Anything related to the security sandbox model of the Java platform? Yeah. 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 So basically the case was that the library was trying to do a reflective call in order to unmarshal a JSON. And the security manager that was running inside the OSGI container did not allow the library to do reflective calls. So the library was loaded in a one class loader, in a separate OSGI class loader, then the one loaded by the OSGI container. So the effective set of permissions that this library had was the intersection of the permissions imposed by the security manager of the OSGI container and the set of permissions for the library itself. And since the set of permissions for the OSGI container did not allow reflective calls, this raised an exception in the library. No, it basically does not change, but the library... Yeah, so basically the fact was that, for example, the one thing was that the library could have provided this just a different way to implement the same logic without reflective source code. And this would actually prevent the security manager exception. So this is one thing. But there are, of course, certain cases where, for example, your library will need to do, or the JSON library will need to do, well, I have a security manager installed, then I need to check for a permission in order to raise a more proper exception for the client. And the exception that was raised by the reflective call was something like no reflective permission, which was very confusing for the users of the library, as you can see here. Okay, another questions? Okay, if not, then thank you for attending this talk. I hope you learned something useful and something that you can apply in practice. Yeah, and the guy that answered the question, please come and get the book.